Hi friends, in this series of network theorems, in this class we will be studying how to apply maximum power transfer theorem. This theorem is not used for solving any circuits but as condition for designing of very high power amplifier circuits, radio transmitters, etc. Here we have connected one speaker to the output of this amplifier. You can see from this information written here that the impedance of this speaker is 8 ohms. That means maximum power will be delivered from this amplifier to the speaker when we will connect this 8 ohm speaker to the 8 ohm output. See, this is the common point and this is the 8 ohm impedance. Instead of this, if it was a 4 ohm speaker, we have to connect it between common and this 4 ohm. This is the side view of this speaker. Same is the case of radio transmitters also. This radio transmitter output impedance must match to the antenna which is connected at the output. In some cases, the output impedance will not be matching with the impedance of this antenna. In such cases, we will be using antenna tuning unit to match the impedance of both for maximum power transfer. You will understand more when we are going through the definition, explanation and doing some examples. Maximum power transfer theorem. So here is a circuit or network which delivers power to a load connected between A and B. Maximum power transfer theorem states that maximum power is delivered from this circuit when the load resistance or impedance is equal to the Thevenin equivalent resistance or impedance of the source. That means we have to first find out the Thevenin equivalent circuit and the maximum power will be delivered when RL becomes this RTH. Here we will be getting maximum power, not efficiency. So now let us see steps for applying maximum power transfer theorem. First of all, we have to remove the load resistance RL from the given circuit so that our circuit becomes like this. See, this RL is removed. Next step is we have to draw the Thevenin equivalent network of the circuit after finding the VTH and RTH. So now the Thevenin equivalent circuit is like this, on the output of which this load resistance is connected. IL is the load current. So as per this power transfer theorem, we have studied that for maximum power, this Thevenin equivalent resistance must be equal to the load resistance, that is RL is equal to RTH. We know that I is equal to V by R. Here V is VTH and the total resistance is this Thevenin resistance connected in series with RL. So I max is equal to VTH divided by RTH plus RL. As this RTH and RL are equal, so we can write it like this: RTH plus RTH, that is 2 RTH. So I max is equal to VTH divided by 2 RTH. Then power is equal to I squared R. So P max is equal to square of maximum current into RTH. So I max we found as VTH divided by 2 RTH. We can substitute this value here. Then this becomes like this: I max is equal to VTH divided by 2 RTH square into this RTH. Removing the bracket, this becomes VTH square divided by 4 RTH square into RTH. From this one, we can cancel one RTH in the numerator and one RTH in the denominator, so that P max becomes VTH square divided by 4 into RTH. In this example, we are asked to find the value of resistance RL in the circuit shown below for maximum power transfer, and we have to calculate the maximum power transferred to this load. For calculation of maximum power transfer, we have to use Thevenin's theorem. For drawing Thevenin's equivalent diagram, we have to find the Thevenin's voltage VTH and RTH. First we will find the RTH. For finding the Thevenin equivalent resistance RTH, we have to remove this load resistance. Then we have to short all the voltage sources. See here, this 3 volt, 6 volt and 10 volt is shorted, and we have to open if any current sources are there. In this circuit, there is no current sources. After removing load resistance RL and shorting these voltage sources, our diagram becomes like this. See here, this 3 volt is shorted, 6 volt is shorted here, and 10 volt is shorted here. Now we have to calculate the Thevenin resistance RTH. Here as this 2 ohm and 2 ohm are in parallel, which is coming in series with this 2 ohm. We can write RTH is equal to 2 ohm in parallel with 2 ohm plus this 2 ohm which is in series. This gives the value 3 ohm. So RTH is equal to 3 ohm. As RTH is equal to 3 ohm, maximum power will be transferred when RL is equal to RTH, which is equal to 3 ohm. Next we will calculate VTH. So in our diagram, as this load resistance is removed, VTH is coming between points A and B where the load resistance was connected. In this one, we will take this mesh and we will find out the mesh current flowing. Let I is the mesh current flowing in this mesh. Applying KVL to this mesh, for applying we have to mark the polarities of currents flowing in these resistances. As current is flowing in this direction, see here current is entering, so it is plus and this is minus where it is leaving. In this resistance, current is entering here and here it is leaving, so it is minus. In this voltage source, it is minus to plus, so rise in voltage, while here fall in potential is there. Then writing equation for this mesh, as current is flowing in this direction, here it is rise in potential, so it is plus 3, then here it is from positive to negative, so in this resistance it is a voltage drop of current into resistance 2I. So as it is voltage drop minus 2I, then again here also it is voltage drop minus 2I, here it is fall in potential plus 2 minus 6, which is equal to 0. Solving this equation, we will get I is equal to minus 0.75 ampere. Then writing the VTH equation here, VTH equation, here it is rise in potential, so 6, then minus to plus, so plus 2 into current is I, then here plus to minus, so fall in potential minus VTH, then again fall in potential minus 10 equal to 0. As the load is open, no current is flowing in this way, so we need not consider this 2 ohm resistance. We know that I is equal to minus 0.75. We can substitute the value of I here. So the equation becomes 6 plus 2 into minus 0.75 minus VTH minus 10 is equal to 0. Solving this equation, we will get VTH is equal to minus 5.5 volt. As VTH is minus 5.5, it means that B is the positive terminal while A is negative terminal. Next we will calculate load current for maximum power transfer and then P max. See, as per maximum power transfer theorem, we have found out that RTH is equal to 3 ohm. So this is equal to 3 ohm and this VTH we found as minus 5.5 volt. That means the battery position is changed. So it is 5.5 volt. As per maximum power transfer theorem, we studied that maximum power will be delivered when RTH is equal to RL. So load resistance RL is equal to this Thevenin equivalent resistance RTH, which is equal to 3 ohm. As VTH is equal to 5.5 volt and RTH is equal to 3 ohm, maximum power transferred P max is equal to V squared TH divided by 4 into RTH, that is equal to 5.5 square divided by 4 into 3, which is equal to 2.52 watts. So the maximum power delivered from the circuit to the load is 2.52 watts, and at that time load resistance will be 3 ohm, which is the Thevenin resistance. In the second example also, we are asked to find the value of this load resistance for maximum power transfer, and we have to calculate the maximum power delivered. For that, first of all, we have to remove this load resistance so that our figure becomes like this. See here, between A and B, the load resistance is removed. Next, we have to calculate RTH, Thevenin's equivalent resistance. For calculating RTH, first of all, we have to short circuit the voltage sources. Then, we have to remove or open circuit the current sources so that our figure becomes like this. See here, 8 volt and 10 volt are short circuited and this 4 ampere is removed from here. In this circuit, this 5 ohm and 5 ohm are in series. That is, this becomes 10 ohm, which is in parallel with 1 ohm. Therefore, RTH is equal to 5 plus 5, which are in series in parallel with 1 ohm. That is 10 ohm in parallel with 1 ohm, which gives the value 0.91 ohm. So, RTH is equal to 0.91 ohm. Next, we will calculate VTH. VTH is coming between terminals A and B, and let A is the positive terminal and B is negative terminal. As here it is open, a current flows here and let it be in clockwise direction, and another current flows in this mesh. Let I1 is the current flowing in this mesh and I2 is the current flowing in this mesh. As this I1 is flowing in this direction and I2 in the opposite direction, we have to take the difference of I1 and I2. But here I2 and this 4 ampere are in the same direction, so naturally I2 will be higher. So we can write I2 minus I1 is equal to 4 ampere. Let this is equation number 1. As current is flowing in this way, it is entering here, so it is positive, and leaving here it is negative. Current is entering here, so it is positive, then leaving here negative. Likewise, here it is positive and this is negative. Now, when we are applying KVL to the outer path, here as current flow is in this way, it is rise in potential plus 8 volt. Then here in 1 ohm, IR drop is there, voltage drop of I into R, 1 into I1, that is from positive to negative. So it is minus 1 into I1. Here also positive to negative, voltage drop minus 5 into I1. Here voltage drop is minus 5 into I2, minus here plus to minus, fall in potential minus 10 is equal to 0. Simplifying this equation, we will get minus 6 into I1 minus 5 into I2 is equal to 2. Let this is equation number 2. Solving equations 1 and 2, we will get I1 is equal to minus 2 ampere and I2 is equal to 2 ampere. Next, writing VTH equation here it is rise in potential plus 8, then voltage drop 1 into I1, then here it is plus to minus. So minus VTH is equal to 0. Rise in potential plus 8 minus voltage drop 1 into I1 minus fall in potential VTH is equal to 0. This gives VTH is equal to 8 minus 1 into minus 2. This is equal to 10 volt. Therefore, VTH is equal to 10 volt. So we got RTH as 0.91 ohm and VTH is equal to 10 volt. RTH is equal to 0.91 ohm and VTH is equal to 10 volt. So we can draw the Thevenin's equivalent diagram as we got VTH and RTH. Here VTH we got as 10 volt and RTH 0.91 ohm. Next, we have to calculate load resistance for maximum power transfer and Pmax. As per maximum power transfer theorem, we know that this load resistance must be equal to RTH. That is, for maximum power transfer, RL is equal to RTH, which is equal to 0.91 ohm. That is, for maximum power transfer, RL is equal to RTH, which is equal to 0.91 ohm, as RTH we got as 0.91 ohm. Next, maximum power delivered to the load is VTH square divided by 4 into RTH. This is equal to VTH square that is 10 square divided by 4 into 0.91, which gives 27.47 watt. In this example also, we are asked to find the value of the load resistance for maximum power transfer to this load. Also, we have to calculate the maximum power delivered. Here, these two resistances are in series, so that we can add it and it becomes 15 ohm. Similarly, these two resistances are in series and it becomes 18 plus 9, 27 ohm. So that we can redraw this circuit as like this. This is this branch, this is this branch, and this 5 and 10 added comes here, 15 ohm. Similarly, this 27 ohm is here and this 27 ohm is here, and here comes 27 ohm, which is got by adding these two series connected resistances. This delta connection can be redrawn like this, these 315 ohms connected. Similarly, this delta connection also can be drawn like this. For simplification, we will convert this delta connection to star connection using the formula delta to star. That means the value of this star connected resistance is product of the two resistances coming on both sides divided by sum of the three resistances. So after converting like that, this delta connection becomes as like this, and this delta connection becomes like this. Now we can redraw this figure like this. This delta connection we have converted to star, and the other side the delta connection is converted to star. Now our figure becomes like this. Next we will calculate RTH. For calculating RTH, first we have to remove this load resistance. Then we have to short circuit any voltage sources and open circuit any current sources. Here no current source is there, only this voltage source is there which we have shorted. So now our figure becomes like this. See, this load resistance which comes between A and B is removed, and in between A and B comes RTH, and this voltage source is short circuited. We can simplify and redraw this circuit as like this. See, in the top this 5 ohm RTH and 9 are coming. In the middle portion, first 5 ohm, then it is connected to this 9 ohm and comes here. In the bottom, this 5 ohm, 20 ohm and 9 ohm are connected in series. In the middle portion, as 5 and 9 are in series, the total resistance is 14, while here these three are in series, which gives 34 ohms. So this can be drawn as 5 plus 9, 14, and sum of this 34. As these two branches are in parallel, this 14 is in parallel with 34, it gives the value 9.92. Now this figure again can be simplified and drawn as like this. This 5 ohm, then this 9.92, and in series 9 ohm. So RTH is the sum of these three series connected resistances. RTH is equal to 5 plus 9.92 plus this 9, which is equal to 23.92. Therefore, RTH is equal to 23.92 ohm. Next we have to calculate the VTH. See, in this figure, VTH is coming between points A and B. As this branch is open, no current is flowing in this branch. So current I is flowing from this direction through 5 ohm, this 5 ohm, 20 ohm, 9 ohm, again this 9 ohm, and coming back to 100 volt. We know that IA is equal to V by R. Here voltage is 100 and resistance is the sum of these series connected resistances. This gives 100 divided by 5 plus 5 plus 20 plus 9 plus 9. This is equal to 2.08 ampere. Therefore, I is equal to 2.08 ampere. Then writing this VTH equation, here we will first mark the polarities. Current is coming in this way, so it is entering here plus minus. Then let terminal A is plus and B is minus, and as it is leaving here it is plus then minus. As this is an open circuit, we need not consider this 5 ohm and 9 ohm. Then writing the VTH equation, there is rise in potential 100 volt plus 100 volt 100. As it is plus to minus, voltage drop minus 5 into I, here also plus to minus, that is fall in potential minus VTH, then voltage drop minus 9 into I is equal to 0. Solving this equation, we will get VTH is equal to 70.88 volt. Next, we have to calculate RL for maximum power transfer and the maximum power transferred Pmax. For that, we will draw the Thevenin's circuit. See this RTH and VTH we found out, and VTH is equal to 70.88 volt and RTH is equal to 23.92 ohm. As for maximum power transfer theorem, for maximum power transfer, this RL must be equal to RTH. So, RL is equal to RTH, which is 23.92 ohm. Maximum power Pmax is equal to V square TH divided by 4 RTH. This is equal to VTH is 70.88. 70.88 the whole square divided by 4 into RTH, that is 23.92, which is equal to 52.51 watt. I think this class also might have been useful to you. If you found any difficulty in understanding any terms used in this class, you can refer to my previous classes, the links of which are given below. Thanks for watching. Please like it, share it and subscribe it by pressing the bell button so that you will be getting all the notifications of my future videos also. See you next time. Bye.